Hello, my name is Rob Reynolds. Welcome to Mat-073. We're in Chapter 3, looking at the very first section, 3.1, and today's topic is solving systems of equations, and we're going to look at the graphing method. There's several ways to solve systems of equations, graphing being one of them. We're going to learn later substitution, linear combinations, and even use matrices to solve systems. But today, we're going to graph two lines, find a nice point of intersection. This line, both the blue and the red line here cross at 3, 0, and that means that if you were to plug in a 3 for the x value, you'd get 2 times 3 or 6, plus 0 equals 6. That's a true statement up here. And if you were to plug in 3, 0 down here, 3 times the 4 is 12, plus 0 will give you 12. That's a true statement. So this point satisfies both the blue and the red, and that's why it's called the solution for the system. So the easiest way to do this is by graphing. We've learned a couple different graphing methods. Y equals mx plus b, the start value is the y-intercept. So you could put a point on the y-intercept here at 1, and then this is my slope, which is rise 3 over 1. So I'll rise 3 over 1, and instead of going up and to the right, you could go down 3 and to the left. I would recommend you fill up the graph with as many points as possible. And then this line is called standard form. It's in the form ax plus by is equal to c. And if you've watched my earlier videos, I've introduced a definition. Monkeys wouldn't prefer apples over bananas to find a quick slope of this, but maybe we'll get lucky by x and y-intercepts. So to find an x-intercept, you let y be 0. And to find a y-intercept, you let x be 0. So let's let y be 0 first of all. If you let y be 0, this whole term drops out, and you're left with x equals 3. Unfortunately, if you try to find the y-intercept by letting x be 0, that'll wipe out this term, and you get something pretty impossible to graph. Negative 3 halves. I don't even want you to try. So let's go to the slope, which is the negative a over b term. And so if I do the a term being a 1, so negative 1 over the b term, negative 2, is 1/2. All I really need is one nice point, which I have at 3, 0. I'll go back to the red for this second line being the red. So we found a nice point, 3, 0. And then I'm going to do my slope, which is rise 1, run 2. Instead of going up and to the right, I could go down and to the left, down and to the left. And that's why I say fill up the graph, because oftentimes you can see pretty clearly that your points will overlap each other, and then that will be your point of solution. It's a terrible line. So it looks like my point of solution, if I'm reading this correctly, start at your origin, go 1 to the left, and 2 down. So we'll name this point right here. Looks like that point is negative 1, negative 2. So my solution is an ordered pair, negative 1, negative 2, which means if you were to plug those in to either equation A or equation B, it will satisfy both systems. And the author agrees, negative 1, negative 2. They actually plotted the point, negative 3 halves. I wouldn't recommend that because that's very difficult to get accurate. So if the two lines are given in slope-intercept form, that makes it a little bit easier. This is a start value, so start at 2, rise 3, and run 4 is your first line. And again, I would go down 3 and run 4 to the left and fill up your graph. So there's line A. Line B is starting at negative 3, but it has the exact same slope. It's still rise 3, run 4. And notice if it has the exact same slope, then the lines are parallel. So we've learned in a previous video, same slope means parallel lines. So this actually has no solution. The lines will never intersect. So we'll say that's the empty set. So if two lines are parallel, we say that the system is inconsistent and has no solution. So consistent means it has at least one solution, usually just one. So consistent means it's consistent with what we think is going to happen. We end up with a solution. Inconsistent means that I have parallel lines and no solution. So let's look at another example. I'm going to graph line A in red using x-intercepts and y-intercepts. So to find an x-intercept, I let y be 0, which will wipe out the 8y term. If I divide by 4, I'll get a 4 for the x term. Then I'll go back and I'll let the x term be 0. And if I let x be 0, that'll wipe out the 4x. And if I divide through by 8, I'll get a 2. So this one was nice. I don't need to actually find the slope. I could actually just plot the 2 points, 4, 0, and 0, 2. If you wanted to find the slope, I could easily enough, very quickly, without even solving for y. I could use the monkeys wouldn't prefer apples over bananas definition. So it's the opposite of the first term over the second term, which reduces to -1/2. And I can actually check down 1 over 2, and I'm creating more points, so it's easy for me to identify all the points. So instead of going down and to the right, I could go up and to the left. Here comes another point of intersection, up 1 and 2 to the left. Again, I'd recommend filling up the graph. So that is the line for, we'll call that line A. I'll label it line A. Line B I'll do in green because I've used most every other color. So B I'll also do by x-intercepts and y-intercept. If you would like to solve for y, you could. But I found that students are a little bit more successful graphing x and y-intercepts. So to find an x-intercept, you let y be 0. That'll wipe out this term. If I divide through by 2, 8 divided by 2 is 4. To find the y-intercept, I let x be 0. And if I let x be 0, that'll wipe out the x term. And dividing through by 4, I'll get a 2. So again, I get 4, 0, and 0, 2. It's the exact same line. So line A is equal to line B. That means every point on line A also satisfies line B. So there are infinitely many solutions. Just the opposite of our last example, which was there was no solution. So if you have infinitely many solutions, that means everything that's a solution on the one equation is also a solution for the other equation. So let's review. If we have one solution, it's called consistent and independent. If we have no solution, it's inconsistent and independent. And if we have line A falling on top of line B, we have infinitely many solutions. Remember, consistent means we have solutions. So we have solutions for A and C. Here's one solution, here's infinitely many. That's what consistent means. We have solutions. Independent means there's different solutions for the green line than from the purple line. There is one point that's the same, but mostly they're independent points, and these are definitely independent points. So that's what independent means. Dependent means that one line falls on top of the other line. So those are the three scenarios that could happen. You could have either one solution, no solutions, or infinitely many solutions. Let's look at another scenario here. I would let this maybe be y sub 1, and this maybe be y sub 2, and write some equations. We want to know, when does y sub 1 equal y sub 2? So you kind of end up with, again, graphing. It says solve it graphically. In a later video, I'll show you ways to solve this by substitution method algebraically. But to graph them, we actually need to start at the y-intercept of -2 and rise 1, run 1, and I'll fill up the graph. Instead of going up and to the right, I'll go down and to the left. So I'll call this line A. And now line B, I'm going to rearrange this just a little bit. It's the same thing as saying negative x plus 6. Again, I was just trying to force it into the form y equals mx plus b. So I can see that the start value is 6, which is actually off my graph. But then the slope is the number in front of x. And so here the slope is negative 1, which means go down 1 and always run to the right. So I'll go down and to the right, and I'll repeat that until I find a point of intersection, which I did right here. Seems like it's over 4 and up 2. So I'm going to call this point 4, 2 the solution, and the author agrees. The last example I put in here because it's very difficult to graph, maybe not line A, but I think line B is pretty difficult to graph. So I'm going to pull out a graphing calculator and show you that one more time like I did in a previous video. So to graph line A, let's just try x-intercepts and y-intercepts because it's in that standard form. The x-intercept, let y be 0. So all of this will drop out because negative 2 times 0 is 0. If I divide through by 6, I don't like 2 6 reduces to 1/3, and again, I would not recommend graphing the x-intercept of 1/3 and 0. You just won't be accurate enough and your graph will be off a little bit. But let's go find the y-intercept by letting x be 0. And if we let x be 0, the x term will drop out, leaving me with dividing by negative 2, and I'll get a negative 1. And that's a nice point, so I'll plot 0, negative 1. But I need another point. So I'm going to go back and find my slope by doing monkeys wouldn't prefer apples over bananas definition. I'll do the opposite of the a term over the b term. Remember, this is in the form ax plus by is equal to c. So the a term is 6 and the b term is negative 2. And that gives me a slope of 3 or positive 3 over positive 1. So that means rise 3 and run 1. Rise 3 and run 1. And I'll fill up the graph. Instead of going up and to the right, you go down and to the left. So I'm looking for any one of those points for line B. Well, when I look at line B, using x-intercepts and y-intercepts, you can spend the time to do this. They're both pretty bad. The x-intercept turns out to be 1/9, 0, which I don't want to plot, and the y-intercept turns out to be 0, negative 1/3, which again I don't want to plot. So I could go to my calculator and try to solve this thing for y and graph it and then look at the table setup, which I've shown you in an earlier video. But let's look at the slope before we do all that. The slope is negative a over b. In this case, the slope is negative 9 over negative 3, which is 3 again. And I notice that it's the exact same slope from my first equation. So if the slopes are the same and I have different y-intercepts, because here's my y-intercept and it's different than the first line. So if I have different y-intercepts but the exact same slope, I know that I'm going to end up with parallel lines, which means no solution. I hope you found this video helpful. Email me with your questions. Thank you.